Okay, thanks. So good morning, everyone. I'm Guilherme. I'm a solutions architect here at Huawei, and I'm going to present our graph engine service. First, I'm going to talk a little about the context of the project. The meeting was reporting to SEPRA's Superintendent of Tax and Labor Affairs, Elaine, and her commercial and technical team. So we would have to deep dive into the solution, in the technical parts of the solution, but also maintain a speech for the commercial team to situate also. And the context a little more is that SEPRO has acquired HCS and is a reseller of Huawei Cloud from both public cloud and their HCS, which is Nuvem de Governo. And some SEPRO Gov customers showed intentions to buy a graph solution, and we need to show them why GS is better, right? That this is the context. So adding GS to HCS is a huge opportunity, as we can see here, right? Let me see if I can, here, yes. Because the data is sensitive, we're talking about governmental customers, and they would like to store the data inside a private cloud, SEPRO's private cloud, right? So they want to know more about our solution and the advantages over other competitors or a graph solution. These governmental customers are all federal tax and financial administration bodies from Brazil's government. So we have Receita Federal, which is responsible for country's tax and custom administration, Bacen, which the main function is to guarantee the stability of our currency, Secretaria do Tesouro Nacional, STN, responsible for managing public finances, and PGFN that represents the union in tax matters. So these four customers are customers from SEPRO, and they think they would like that SEPRO has a graph solution inside HCS. Okay, so now let's get into the presentation, right? Basically, when we're talking about graphs in a general way, these are graphs, okay? So we have a pie graph, we have a column graph, but when we are talking about computer science, these are not graphs, okay? These are charts or plots or even graphics, because when we are talking about computer science, graph is a whole different thing. This is not a graph. This is a graph. It's a data structure that we have nodes, which are these circles, and edges, which are these lines. This is a graph. It's this data structure. The nodes represent entities, right? So it can be people, places, companies, and the edges represents the relationships between these entities. So it could be this graph could represent like friendship network. So number one is friend of number two, but number two doesn't consider number one his friend. It could be something like this. Okay, this is a graph. Okay, but now that we define a graph, why should we use a graph database? Why is that necessary? What are the application scenarios that we should use a graph database instead of a regular relational or NoSQL database? Well, a graph database can solve problems that cannot be solved by relational databases and other NoSQL databases, right? Like key value database. Here in the graph database, the connection is as important as the data itself. So the relationships are really, really important also, not only our entities. I can highlight here that these relational database and key value database have poor in-depth analysis performance. So the performance when we have a lot of sequential relationships is very poor, it's bad. So a graph database comes to solve this issue, basically. It has a high performance in-depth analysis and complex transactions because we have the data structure made, right? So the connection is as important, and because we have stored on its nature, it's from the data structure itself. If we use a relational database, right? A traditional database, for example, every single time we made a query that has this in-depth analysis, we would have to make a lot of complex joins, for example. So this is slow and computationally very expensive. So the graph comes to solve these issues. The graph analysis and database is also really important for enterprise and machine learning and big data scenarios. But here, what I want to highlight in this slide is we have two major graph models, which is the graph database, which is the responsible for OLTP, the CRUD, basically, and stores the data, right? And the graph computing engine, or only graph engine, which will OLAP analysis, high-level algorithms already to perform this OLAP analysis, right? So we have these two major models in the graph database. They are must-haves for increasingly diverse big data, and especially for heterogeneous computing. So we have heterogeneous service data stored in different databases, different data structures, data types. A graph is very good for these scenarios because we can do labeling. When I say labeling is when we have nodes, we use label for saying which entity is it, right? If it's a person, if it's a company, or whatever. So here, this line, you can see the evolution until we get to diversification and heterogeneous computing for machine learning and using graph database and specifically graph analysis engine, which is really good for machine learning scenarios and big data. And also we can see here that graph database engines, they are growing really fast in the market. So this line here is for graph database. We can see it's an engine that is really growing fast. I don't know if my internet is a little bad, but okay. So in which scenarios is a graph database and analysis required? We can highlight here scenarios where we have hundreds of millions of billions, even a trillion data for edges. So a graph database is recommended in these scenarios, mainly because of its performance, right? So also, like I said before, in-depth analysis, this is a key point. We have a comprehensive analysis of data from multiple dimensions. And we have also some specific industry scenarios, right? For a government, we can do a detection of potentially sensitive events. For finance, we can have anti-fraud, anti-money laundering, risk analysis. For device management, which is the electrical network topology, for internet, recommendations for e-commerce, recommendations for social media. We're going to talk about this later. And for material management also, BOM is the bill of material, right? So it's like the recipe of our product. We can also structure this as graphs. And we're passing through evolution of graph. It's not only for correlational query and community analysis anymore. Graphs will be the foundation of future AI because we can, for example, I'm going to talk this later, but we can use a graph with vectors, which is really good for embedding, and we can apply this to machine learning models. I'm going to talk about this later in the presentation. But here we can see that we have knowledge graph, gene graph, device graph. They're all very important in AI scenarios. And also, we already use graph databases and graph analytics in our daily life, and we might not even know. So, for example, if you access TikTok or Instagram and you are in social media, right? And then you enter it, and it gives you users that you can be friends with, right? Or content that you might like. In the background, the platform is using a graph for this. Also, for shopping, everyone here already use Mercado Libre or Amazon, Taobao, I don't know. But every time you buy a product, let's say I buy a computer, every time in the end it says people who bought this also bought or frequently bought together, right? This is possible due to graph analysis, right? So, and also for search, for we can so we can deliver relevant search results in Wikipedia and Google. Graph is currently really present in our daily life, and we might not even know. Okay, so now we understand why we should use a graph database, but why specifically, why specifically Graph Engine Service, GES? Why specifically our Huawei Cloud solution? So let us see the contents of our solution. Firstly, what I want to highlight here is that we have AWA kernel. I don't know if that's the correct pronunciation, but the AWA kernel integrates both graph database analysis and visualization capabilities all in one. So we can say that GES is a one-stop platform that joins, groups all these features, right? We can see here in the diagram. So we have the graph analysis algorithms already natively in our service, more than 20 in-depth optimized algorithms for multiple industry and case scenarios. We have the graph database, of course, that will store the data, and the graph visualization, as you can see here, it's our graphical interface, wizard-based, and we can use when we can apply our algorithm operations and play a little with our graphs. I'm going to show it in the demo, and it's really, really nice. So we have all this in a one-stop platform. Big data integration, we have it seamlessly. Why? We can use real-time online data and offline data to feed our GES, right? We have this natively also. We can connect OBS and things like that to our GES database, and then we can perform the analysis through the graph engine, okay? We have complete filtering and query functions, like I said, with more than 20 graph analysis algorithms. And here we can see that our efficiency, we can see that the performance compared to some competitors are really high. Our performance is really good. For example, if for 2-hop query, we are 2 times better than the others. For 3-hop query, we have 36, and the second one is Graph, which is also a very good competitor, right? It has only 9 in this 3-hop query. Also, here we use it says the page rank. It's an algorithm. We're going to see it in the demo. For shortest path and page rank, we also have a better performance. So, like I said in previously, the performance is one of the biggest key points. It's not the biggest, it's not the one, right? For graph database, because it's all about performance, basically, right? So, and these tests were performed using Twitter database, so it's like billion edges, right? So very nice, this performance we have. Also, Graph DSL, what can we say about it? DSL is a proprietary language that supports query and algorithm. We also support Gremlin and Cypher, which are the 2 most known and used languages for query. Gremlin is for graph traversal, which is from Apache Tinkerpop, I think. And Cypher, which is the biggest one, it's for Neo4j, and it's a query language. DSL, it's like a combination of both of them with computational models, right? But if you want to use Gremlin, if you want to use Cypher, and you don't care about our DSL, which, I mean, it is recommended to use it, but if you don't want to use it, you can use 3. You can use the 3 options, right? It's up to you. Here's just an example of how we can implement an algorithm. I think it's PageRank, I don't remember, using GraphDSL, right? So it's very simple. Yes, it is PageRank, it's here. The graph visualization is enhanced, so we have a graphic interface that we can play with. We can drag the vertices, we can search for the edges and the relationships, informations. I mean, we have a lot of things. I think this is better to show in the demo. Temporal graph. This one is a really good feature we have in GES. Temporal graph allows us to have dynamic analysis for graph structure. So it's not only like storing timestamp in a graph. We have natively algorithms and features, right, capabilities that will allow us to have a temporal and dynamic analysis. So this is really good for fraud detection, for example. I'm going to show it in the demo. It's really nice. It's really intuitive for in our console, and opens a whole new world of possibilities, right, if we have a temporal graph. Also, a really good thing, we have a fine-grained permission control using IAM, right? It's not only, user X can access or not our graph database. No, we have a fine-grained permission in attribute level and label level. So we can say, like, for example, that someone can query the person, but cannot query its CPF, right? So we can have this control in GS, which matches enterprise organization structures, right? Here is a huge table with our competitive analysis with some other competitors, Alibaba, TigerGraph, Neo4j, which are the biggest one in the market, and Nebula Graph. So I'm not going to show everything here, right? But the main idea, I think the main what we can highlight here is the storage capacity. We can have up to 1 trillion edges. What else? The algorithms. This is something that we have that is really good because we have already in our platform, we have the native, we have already some algorithms that you can use. You don't have to create a code using Cypher or Gremlin or DSL. You already have some of them implemented to you. And the other ones don't have that much, or for example, this Alibaba doesn't have it. The query performance is very high. The algorithm performance is very high also. These native algorithms are really fast. And we can say that we can highlight the cloud architecture, right? It's cloud native. It's not only a full stack cloud solution, it is cloud native. So it gives us a lot of capabilities. Also, we can highlight here its scale without performance degradation due to exactly its distributed architecture, right? We can highlight also the high throughputs we have, the multi-hop for in-depth analysis to detect fraud, identify communities, optimizing routes, and also our comprehensive library of algorithms. Like I said, we already have some implemented, so you don't have to waste your time implementing it, right? We don't have to reinvent the wheel. If we already have an algorithm, we can just, we already provide to you some of them. And the performance here, we can see like some of the algorithms. The label propagation is 4 times better than TigerGraph and 40 times better than Neo4j. It's really high. The shortest path really used algorithm. It's 7 times better than TigerGraph and 50 times better than Neo4j. And PageRank 3 times better than TigerGraph and 1.5 times better than Neo4j. Okay, so now we're going to talk about some success cases that I would like to talk. First, smart financial risk control. It's a pity that we cannot say the customer because for compliance reasons, right? But this one is really nice. we can use this for risk control in financial, and we could apply this to tax scenario, right? Too, right? So the benefits was like in this the bigger search scope, we could improve the hops. So it's like instead of 2 hops, it's now 5. We have a rapid response to 6 hop queries, which is a lot. We have it in seconds, and the efficient detection of guarantee risks is it was 10 minutes, and now it's 1 minute. But what I like to say here is that we have made this already. So for the customers, for the tax and financial customers, we already have this success case in production, right? We're not talking about what we could do with GS. This is what we did. So this is a real case that happened, and we did it. We performed, we've implemented together with the customer this solution. So for Sapro's customers, right? Sapro financial customers, we could do this, how can I say, like this transfer knowledge seamlessly, because we already had this made. I think it was in China, but I'm not sure. We already have made this in production. It did happen, right? So this transfer knowledge, this transfer knowledge share would be seamless, right?
5 minutes.
Okay, thanks. Also, we can highlight this scenario, which is for public security cases. So let's suppose that a criminal performed a robbery, I don't know. And you can see, you can use GS along with the cameras in the city, I don't know, to see which places he went, right? In a very fast way. So it was like 3 hours to detect this criminal. Now it's 20 minutes in this specific case. So the graph analysis GS perform is really good for this case also. Other case for FAW Volkswagen. FAW Volkswagen is a joint venture from obviously FAW and Volkswagen, right? And it's a BOM, like I said before, it's a bill of materials scenario, which means that it's the recipe of our product. So we have our final product, vehicle, we have our parts, our subparts, more subparts, more subparts, until we get to the raw material, right? So this is only like a 4 hop, but we can think that it's not that simple. It's not that small. It's just a representation, right? So the in-depth analysis can be really, really huge. So the performance was for changing to GS was really, really high. And for last, I want to highlight this one because it's for VMAL, and it uses both real-time recommendation and offline recommendation. So real-time recommendation, it shows us the friends of our friends using query and algorithms. And here we use the node to back. Like I said, it's an algorithm embedded in our platform that transforms our nodes or vertices in vectors. So it's a really good input for machine learning models and deep learning, of course. So they exported the outputs of these algorithms and use it as an input for machine learning models, external machine learning models, right? So I think we can go to the demo. The little context about what I'm going to do is a tax fraud evasion situation. So the idea here is to leverage GS capabilities to uncover tax evasion based on short-lived shell companies, right? And we're going to use, like I said, the native temporal analysis to see the chronological sequence of the fraud. So that's it. I'm going to go to the demo. Okay, everyone can see my screen, right? Here I am in the console, Huawei Cloud console, and we have our graph engine service. And I already have my graph created because it takes a little time, right? There's a big database with billion edge capacity. I mean, this one is million edge, but right, it's still big, right? So I already made this, but I can show, I'm going to show a little about all these things. We can have an overview of all our all our graphs existed. So right now I only have one, right? This graph management, which we will see a little later. The backup management, we can perform backups of our graph instances. The metadata management, where we will upload we will create by a file, an XML file, I don't know. It will be the schema of our database, right? So basically the schema, this term is very used in relational databases. It's the same thing here. We're going to define the structure of it. Task Center, it shows us creation, deletion, important of data into our graphs. It shows all the graphs I already made. You can see that it's a lot. Connection management, it has a native capability of connection with JDBC. We have this private URL. And granular permissions, like I said, for IAM into our service, right, into our graph instances for label and attribute level. Okay, so when we create a graph, it shows us some things. Not going to create, I'm just going to show how I did. Here, we can see that it's we can create a dynamic graph or customize a graph. I used here because it's a dynamic graph. I want to do a temporal analysis, right? So it's very simple. Here you just have to put a VPC, subnet security group. If you want to use an IMP to connect it to the internet, you can use TMS or tag management service. You can encrypt data, which gives us a layer of security, really good, because for the user, it won't be encrypted. Like it will, we can see it, it's not encrypted, but for external users, users that don't have permissions, for example, it will be encrypted for them. If we traverse these requests in the internet or whatever, it will be encrypted. We can also have the cross AZ, high availability, and Cepros HCS already has more than one AZ, so this is a function we could apply to HCS and provide high availability, and some other things that the graph size, right? But I'm not going to create because I already have one. So what we're going to do is access our graph database. When we access, we are seeing our graphic interface. Okay, so here I'm going to skip this part for now. Firstly, I want to show here is the algorithms we have, right? And here's our temporal algorithms we have. It's only 3, but they are really useful for a lot of scenarios. And we have our static algorithms also. I'm going to run PageRank, which will tell us the influence, the relevance of our nodes in our network, right? So to run, I just click here. It's very simple. Down here, it shows it's running, if it was a success or not. And here we see our graph, right? Okay, let me tell here. I'm gonna change the color because it's a little bad to see. I'm gonna put red. Okay, perfect. Okay, so here we can see that we have a huge network that seems normal. Firstly, the red dots, the nodes, are persons, and the blue nodes are companies. Okay, so we can see that this is okay. This seems like the normal graph, normal network. The edges represent when we have a connection between a company and a person. It means that the person is a shareholder of this company, and the edges between the nodes of companies means that they have issued invoices, right? So we can see that this seems normal. However, there is another network separated here that calls our attention. Why? We have company 10, company 8, company 7. We have the person 42 and the person 1. This is the strange scenario because person 42 is a shareholder of both company 7 and 8. These companies only issue invoices to the company 10, and the company 10 is owned by person 1. This is, we can't say it's a fraud, but it calls our attention because it might be, right? So this scenario is weird. What can we do? We can go to the temporal page, and we can run the community evolution algorithm. Here, I'm going to put the nodes that are in this weird, suspicious network, right? All of them. And we're going to see exactly the evolution of, in a timely manner, right? In the temporal manner, actually. Let me see if I put everyone, 42, 1, 7, 8, 10. Okay, we're gonna run it. Oh, now we have to put our time because we are going to use the temporal, the dynamic capability of our graph. I'm gonna put the whole year of 2023, which is when the scenario occurred. And okay, then I run here, and it's running. And we will see here. I'm gonna stop. What we have the person 1 is a shareholder of company 10, and what we have here is that company 7 is issuing a lot of invoices to company 10. You can see it. It's according to the time, right? Let me change the date here. Okay, it restarted, but okay. We will start from January 1st, and we can see that the company is sending a lot of invoices to the company 10, which seems to be our money sink, right? Our beneficiary company. Then what will happen? The company 7 will become hot at some point. So this is very common practice in fraud and money laundering. This company will become hot. That means that it will have a lot of issued invoices. So the fraudster, what he do is create another one, close this company, and now this new company will be the responsible for issuing these invoices to our beneficiary company. This is a really indicative that this is a fraud happening, right? We detected a fraud based on our temporal analysis. Due to this capability, right? It closed the other company and opened another one to do the same thing. And this company only issues invoices to this one. So this is a fraud scenario, and we could see it through our temporal graph analysis. And it's important to say that it's not only a static graph with timestamp as an attribute. This is a graph that truly understands time, right? It's not only an attribute, it understands time as something else, something bigger. So this is an advantage of our solution. This natively, we have this temporal analysis, and with no code, we can run some algorithms, right? And also, if we want, we can use here to do some queries in Cypher, Gremlin, or DSL, like our proprietary language, as I said. But basically, that's what I wanted to show in our demo. It's highlight the temporal analysis, temporal capability, what we can do with a dynamic graph, and our visualization platform, right? So I think that's it for my demo presentation.